So in the previous class, we ended the class, but we talked about electron distribution of atoms and things like that. And we ended the class showing you guys how to draw organic molecules, correct? So we talk about we have already discussed about the octet rule, about the Lewis structures. So I want to pick it up right there and give you a couple of problems to solve with me here. So I'm gonna write it on the board. So please take your notebook and write it with me here. And I'll change now the Okay, so what I want you guys to do now is to calculate the number of carbon. So give me, I'm gonna type it in the chat, what's the molecular formula of the compound that is shown on the screen? Okay, so I'm gonna give you a couple of minutes to work on that. Okay, guys. So the answer is correct for C9H19. I'm gonna show it over here for those of you who are still working. So number of carbons, we have one carbon here, two, three, four, five, six, seven, eight, nine carbons. Okay. Number of hydrogens, we have three, two, so it's five. How many hydrogens do we have at this position? One, so that's six, eight, nine. How many hydrogens here? Okay, 10, 11, 13, 14, 17. Okay. Okay, guys. So you gotta practice this. Okay. One of the things that I expect you guys to do is to draw properly organic molecules with. Anybody remember what's the name of this way of writing the molecule? So what's the name of this? Uh, Anybody remember this? So this is a line and angle notation. Correct. So one of the things I expect you guys to do for the exam is going to be to properly draw organic molecules. Okay, so not a secret. That's one of the major goals of this class. So when you get to organic one, so you should be ready um, to really don't have to uh, study this at all. So just by looking at the molecules, you should be able to tell the structure and so forth. Okay, so that's one thing. We practice some more in the next class. So the second thing that I want to show you, so if we want to, so that's the structure of this compound. So what about if I want to draw, if I ask you to draw the Lewis structure of the compound shown on the screen? So what should I do if I ask you to draw the Lewis structure? That's something that you also must know at this point. Anybody remember what is the Lewis structures? When we talk about Lewis structure, you can type it on the chat, please. So when we talk about Lewis structure, what are we talking about? What do we exactly what do we show in Lewis structures?
Valence electron.
Valence electrons, right? So, uh, okay, so for a molecule like this, okay. So here is the thing. Carbon is in group four. How many valence electrons for carbon?
4.
Four, right? So let's say this carbon over here. How many bonds do we have in this carbon over here? How many bonds do we have in this carbon over here, guys? Hmm. Any other answers? How many bonds do we have in this carbon? We have 45 people and very few people are answering. So I want to make sure that everybody is involved, okay? That carbon has 4 bonds. Every carbon in this molecule has 4 bonds, okay? So remember, the maximum number of bonds for carbon is 4 because the valence electrons, the valence shell in carbon is shell number 2, and that is, there are only 4 orbitals in the second shell. So the maximum number is 4. Okay, so carbon has 4 bonds. It has 4 electrons, okay, in the valence shell. So if it has 4 electrons in the valence shell, 4 bonds, uh, that means 4 bonds is 8 electrons divided by 2, that's 4, right? So should I add any dots in a carbon with 4 bonds? Do I require to add any dots in any carbon with 4 bonds? No, right? So I'm gonna type it on the chat in case you guys, so 4 bonds equals 8 electrons, right? So we divide the number of electrons by 2, number of electrons divided by 2, that's 8 divided by 2, which is 4, and 4 is exactly the same number as valence electrons. So we don't need to add any dots there, okay? So that's totally okay. So any carbons, guys, with 4 bonds, no dots needed in Lewis structures. Okay, what about this oxygen here? So how many bonds do you see in this oxygen here? Okay, 2 bonds. Anybody else? Everybody want you guys to be active. How many bonds in that oxygen? 2 bonds. 1 bond to a carbon, 1 bond to a hydrogen, right? So 2 bonds. So 2 bonds accounts for total of 4 electrons. So 4 divided by 2, that's 2 electrons. Oxygen is in group 6. So how many valence electrons for oxygen? 6. So I have 6 valence electrons. 2 bonds accounts for 2 electrons. So how many electrons am I missing in an oxygen? If valence electrons are 6 and I only have 2 bonds, how many electrons do I have missing? 4, right? 4. So remember, once again, I'm gonna write it for those of you who, and if you guys don't get it, just write it and I'll be happy to repeat. So I'm gonna repeat again. So 2 bonds equals 4 electrons, right? 4 electrons total divided by 2, that's 2 electrons for oxygen. 6 electrons in valence shell. So I'm missing 4 electrons. Therefore, to complete the Lewis structure of this oxygen, I am going to add 2 lone pairs, which account for 4 electrons. Okay? What about this oxygen here? How many bonds do I see in this oxygen over here? 2 bonds, right? It's a double bond toward the carbon. So 2 bonds, that's 2 electrons. Oxygen is in group 6, so I am missing 4. I need another 2 lone pairs. Okay? What else do I need to do to complete the Lewis structure of this molecule here? Anything missing? Every carbon, we know we don't, it's with 4 bonds, we don't need to add any dots. What else should I
Nitrogen
add
for
to complete
nitrogen.
the nitrogen, right? So this nitrogen here, how many bonds do you guys see in this nitrogen here? Uh-huh. Any other answer? How many bonds do we have in this nitrogen here? Okay, guys, you're confused because it looks how it's written, right? It's the same thing as if I had said this, and I did it on purpose. Okay, it's exactly the same thing. So don't be confused. If you see in the textbook NH, that means that the nitrogen is bonded to a hydrogen and is bonded to this carbon and is bonded to this carbon. So total number of bonds for this nitrogen is 3. 3 bonds, so it's 6 electrons divided by 2. That's 3 electrons for nitrogen. Nitrogen is in group 5. How many valence electrons? It's in group 5. How many valence electrons? For
Five.
nitrogen,
Five.
5 valence electrons. So if I have a total of 3 and valence electrons is 5, I am missing 2 electrons, so I need to add a lone pair. Okay, now I have the full Lewis structure of this molecule. So when we talk about the Lewis structure of organic molecules, you must give with dots the potential lone pairs. Obviously for carbons, that's not a problem because any carbon with 4 bonds is going to be neutral. No dots needed. However, for oxygen and nitrogen or any other heteroatom, you need to understand that you must count the number of bonds, determine how many electrons for that atom, look for the valence shell of that specific atom, and then determine how many lone pairs you're missing or how many electrons you're missing, which should be added by using dots. And that's actually what will complete the Lewis structure. So I'm gonna write over here, this is indeed the Lewis structure of this compound. Okay. Any questions in regards to this? Okay, I'm gonna give you, so with that in mind, if you have any questions, please feel free to ask or type it on the chat. I'll be happy to answer any potential question. Okay, with that, I want to go over, by the way, guys, in this structure over here, I'm gonna ask also something we talked about in the previous class. How many polar covalent bonds do we have there? Okay, so somebody's asking, it's I think the second time, there are not slides for this class. This class is to be attended live as we are doing now, to be taking notes. The videos are recorded and every video of the class is posted on Blackboard. I don't use slides. I am making this up with you right now as we discuss. I don't have any PowerPoint slides or anything like that, okay? So how many polar covalent bonds do we have here? This class is meant to have like a conversation about, organic chemistry between you guys and me. Uh, how many polar covalent bonds in this? So what's the definition of a polar covalent bond? So once again, so first of all, what's the definition of a covalent bond? We talked about this before. I want to emphasize this today. Definition of a covalent bond. Share electrons, right? When do we have a polar covalent bond?
When we have like an electron negativity from 0.5 to 1.9, we have covalent bond.
Exactly. So when we have a significant difference in electron negativity, particularly between 0.5 and 1.9, okay? Whenever we have that case, we have a polar covalent bond. So in this case, how many polar covalent bonds do we have in this molecule? So even if you don't know the numbers, I can tell you this, okay? Because I want you guys to get used to this. Carbon is in group 4, nitrogen is in group 5, oxygen is in group 6. Which one is the most electronegative of all of them? Oxygen. And next, after oxygen, nitrogen, right? So the order of electronegativity is oxygen, more electronegative than nitrogen, more electronegative than carbon, okay? So I can tell you already the difference in between nitrogen and carbon, oxygen and carbon is equal or larger than 0.5. So how many polar covalent bonds do we have in this molecule? How many, guys? No answer. So nobody knows how many polar covalent bonds we have here? No guess? Okay, so is a carbon-carbon a polar covalent bond? No, right? So what about this carbon-oxygen? Is this a polar covalent bond? Carbon-oxygen bond? Yes, right? So this bond is polarized, and I'm gonna use this arrow to show that it's polarized toward oxygen, okay? And that, once again, because we talked about this in the previous class, I'm gonna color code this. That actually means that there is a partial positive charge. I'm gonna look for the symbol now. So there is a partial positive charge over the less electronegative atom, in this case, a carbon, and a partial negative charge over the most electronegative atom, in this case, the oxygen atom. Guys, this is very important for you to remember and to know. As I said in the previous classes, this is the fundamentals of the reactions in organic chemistry, okay? What about this bond here? It's a double bond. Is this bond polarized? It's also carbon oxygen, so it's also polarized. So we have same as here, it's polarized toward oxygen, and we also have a situation in which, obviously, because of this polarity, there is a partial positive charge and a partial negative charge over the oxygen. Okay, so two polar covalent bonds. What about this carbon-nitrogen bond? Is this carbon-nitrogen bond polarized?
Yes.
It is polarized too. Okay, it is polarized too, because once again, the difference in electronegativity between carbon. So there is a double bond, and we will discuss now some more about that. What kind of bonds are they forming and so forth, okay? But there is a double bond. So here is also bond polarity here, carbon-nitrogen, okay? And what about this carbon-nitrogen? Is this bond polarized?
It's polarized.
It's polarized too, right? So there are four bonds that are polar covalent bonds, okay? And just to show you guys how important this is, okay? This carbon over here is bonded to an oxygen and to a nitrogen. So you can see how this carbon, their partial positive charge here is significantly higher as here because it has two electronegative atoms bonded to it as compared to this one that it has only one, okay? Or this one that is only bonded to nitrogen. And the difference in electronegativity here is not that significant. Yes, the OH, that's a good point. I was talking more about the backbone of the molecule, but you're absolutely right. The oxygen nitrogen bond is also polarized, and the nitrogen hydrogen bond is also polarized. Okay, so that is absolutely correct. Okay, guys, so just wanted to remind you a little bit about the definition of these polar covalent bonds and what they mean in terms of the structure of organic molecules. All right, so next I want to just define something we call in organic chemistry formal charges. And the formal charge is the charge of an atom in a molecular ion. I'm going to type it in the chat. So charge of a specific atom in a molecule or ion. Okay, that's what we define as formal charge. Very important concept to be familiar with. Okay, so I'm going to draw now a molecule here. Um, So to know the formal charge, you have to know the Lewis structure, okay? So I'm gonna draw a different, slightly different molecule here. We are gonna go over this now, and okay. So how do we calculate for a formal charge? Okay, so if you look into our textbook, they will give you a formula, and every organic textbook will give you a different formula. Okay, I'm not a big fan of using formulas to doing and memorizing anything. As I said, this class is about reasoning. So I'm gonna tell you how you should reason this. Okay, so let's focus on oxygen. Okay, oxygen. Oxygen is in group 6, so it has 6 valence electrons. Any oxygen with 6 valence electrons will be neutral, meaning formal charge is 0. Okay. In fact, to make you understand this, let's add carbonyl here so we can actually uh, look into this. Okay. So if we look at this at this oxygen here, okay, the blue oxygen. All right. Okay, so any oxygen with 6 valence electrons will be neutral or formal charge will be 0. Let's see about this blue oxygen. How many bonds do we have in the blue oxygen? How many bonds do you guys see in this blue oxygen? 2 bonds, okay? So if we have 2 bonds, that's how many electrons in 2 bonds total? 4, right? So we said 4 divided by 2 because a bond is in between 2 atoms. That accounts for 2 electrons for oxygen. Okay. How many more electrons do you see in the Lewis structure that I gave you? How many more electrons? 4 more, right? There are 2 lone pairs. So 4 electrons in the lone pairs plus 2 electrons in the double bond. That totals 6 electrons. So what would be the formal charge of the blue oxygen? What will be the formal charge of the blue oxygen? 0, right? Because, as I said, oxygen is in group 6, it has 6 valence electrons. So once again, what I did here is I look into how many bonds, 2 bonds, that accounts for 2 electrons, for 6 electrons, the same number of electrons as oxygen is supposed to have. So this is a neutral. Oxygen formal charge is 0. Okay, so Ruth had a question. Go ahead.
Yes, I had a question. When you ask about a bond, for example, in this case of the oxygen, we also include the pi one, right?
There is a double bond, so 2 bonds, a
Okay,
sigma
two
and a pi.
bonds. Okay, okay, perfect. Okay, thank you. Just to clarify that part. Thank you.
Okay, so that's so everybody understand that the blue oxygen has a formal charge of 0 because there are 6 electrons in the valence shell of that blue oxygen, which is what oxygen is supposed to have. So let's look into this oxygen here. We're gonna color code it as green, and then I'm gonna ask for the green oxygen, how many bonds for the green oxygen? The green oxygen is showing 1 bond, right? So 1 bond, that's 2 electrons divided by 2, 1, right? So how many electrons are according to bonding? 1 electron. And how many more electrons do you guys see in the green oxygen? There are 3 lone pairs, so that accounts for 6. So the total number of electrons in the green oxygen is 7 electrons, correct? So if oxygen is in group 6 and is supposed to have 6 electrons, and this green oxygen has 7 electrons in the valence shell, what would be the formal charge of this green oxygen? It has an excess of 1 electron, and the charge of electron is -1. So what would be the formal charge? -1. Okay? So once again, the charge of 1 electron is -1. Okay? Oxygen is supposed to have 6. It's in group 6. So an oxygen with 7 electrons, it has an extra electron. Therefore, the formal charge of that oxygen will be -1. It has an extra electron, 1 negative charge. Okay? If you guys have questions, please feel free to ask. What about the red oxygen? So the red oxygen, how many bonds do we see in the red oxygen?
2. I mean 3.
Aha. 3 bonds total. Everybody agrees on 3? Or anybody else got something else to say? Everybody agrees on 3, right? 3 bonds. There is a double bond here, carbon oxygen, and there is a bond oxygen carbon here. So total is 3 bonds. Okay. So 3 bonds, that accounts for how many electrons total? 6 electrons, right? So 6 electrons divided by 2, that it's going to give me 3 electrons for oxygen. Okay, how many more electrons do we see in the red oxygen? So I see 3 for the bonding electrons. How many more? That are 2 more, 1 lone pair. So 3 plus 2, that's a total of 5 electrons. Okay, so oxygen is supposed to have 6. It has 5 electrons, that particular oxygen, the red oxygen. So it's lacking 1 electron, right? So what is the formal charge of an oxygen lacking 1 electron? Positive 1, okay? So as a summary of this, guys, an oxygen with 2 bonds is going to be neutral, formal charge 0. An oxygen with 1 bond is going to be negatively charged, which I'm going to now correct. I'm going to add over here because now you know. And an oxygen with 3 bonds has a formal charge of +1. So I'm going to add the positive charge here. So that's where you actually how you should write it. Formal charge here, nothing to write because it's 0. -1 here, +1 here. Okay, what about this nitrogen? How many bonds do we see in this nitrogen? 4 bonds. 4 bonds, that's 8 electrons. Okay, divided by 2, that's 4 electrons for nitrogen. Any lone pairs in that nitrogen? Did I draw any lone pairs there? No, right? So the total number of electrons is 4. Oxygen is in, sorry, nitrogen is in group 5. So I'm expecting 5 electrons in the valence shell. So what is it's lacking 1 electron. So what is the formal charge of that nitrogen? +1. Okay, and nitrogen with 4 bonds will be positively charged. So once again, 5 electrons in the valence shell of nitrogen. It has 4 electrons in the structure. From the bonding electrons, there is no lone pair, so it has an it's lacking 1 electron. Thus, the charge, the formal charge, is +1. Okay. All right. So let me give you another example. So you guys should be drawing with me on your notebooks, okay? Okay, so here is another molecule. I wrote it as a full structure here, full Lewis structure, because the first time that you guys see this, okay? All right, so let's look into the formal charge of the atoms here. What is the formal charge of this carbon here? How many bonds in that carbon? 4 bonds, right? So if a carbon with 4 bonds, that's 8 electrons divided by 2, 4 electrons for carbon. Carbon is in group 4, so what is the formal charge of that carbon? 0, right? No question about that. What about this carbon over here? How many bonds do we see in this carbon here? Okay, anybody else? So 3 carbons, right? 3 bonds, I'm sorry. So 1 bond to the hydrogen, 1 bond to the carbon on the right, 1 bond to the carbon on the left. So the total number of bonds for this carbon is 3 bonds, okay? 3 bonds, and that's the first thing you need to know, how many bonds. So 3 bonds account for 6 electrons. So once again, 3 bonds equals 6 electrons because each bond has 2. 6 electrons divided by 2, that is 3 electrons for carbon. This carbon has 3 electrons in the valence shell. I don't see any lone pair whatsoever. So 3 electrons for the carbon is supposed to have 4. What is the valence shell of that carbon? I'm sorry, what is the formal charge of that carbon? +1, okay? So any carbon, guys, and this is going to be super important. I'm going to put the charge here, type it on the chat because that's super important, okay? So any carbon, so I said the maximum number of bonds for a carbon is 4. Any carbon with 3 bonds will have a formal charge of +1, okay? It's positively charged, and we are going to call this a carbocation. This is one of the words that you will use the most next semester, carbocations, okay? Any carbons with 3 bonds, it's lacking electrons, therefore that's a carbocation, okay? Positively charged. I want to repeat again the octet rule. Every atom reacts to complete 8 electrons in the valence shell. The carbocation is electron deficient. That's why the charge is +1. Is going to react very quickly to complete 8 electrons in the valence shell. So it's going to accept 2 electrons from any species that can actually give those electrons to it. And by doing this, it will complete the electrons and it will be very stable. So carbocations are highly unstable because the octet is incomplete. The valence shell is incomplete. So carbocations are reaction intermediates. You will see that a lot in next semester. So I want you guys to really understand this. Okay, so this carbon has 4 bonds, formal charge is 0. This carbon has 4 bonds, formal charge is 0. How many bonds do we see in this carbon over here?
3 bonds.
3 bonds, right? So 3 bonds will account for 3 electrons for carbon. I also see a lone pair, right? That's 2, so 3 electrons plus 2 electrons from the lone pair. That's a total of 5 electrons. Carbon is in group 5. Sorry, it's in group 4. Supposed to have 4 electrons in the valence shell. This carbon has 5 electrons. So what is the formal charge for this carbon? It has an excess of 1 electron. The formal charge here will be -1, correct? This is also something you will see in organic chemistry, particularly in organic 2. So any carbon with a lone pair and 3 bonds will be negatively charged, and we call this a carbanion. Once again, they are highly reactive. In this case, they will react with electron deficient species because the carbon um, is electron rich, okay? What about this nitrogen here? Gonna color code it as red, okay? How many bonds in that nitrogen? Oh, I'm sorry. The program thinks that I was making a mistake and I was not. So how many bonds do we have in the red nitrogen? 2 bonds, right? So 2 bonds in the red nitrogen, that accounts for 2 electrons. how many lone pairs on that nitrogen, the red nitrogen? So 2 lone pairs, 4 electrons. So the total number of electrons for the red nitrogen is 6 electrons. The gains, why is that? So 2 bonds in the red nitrogen, 1 bond to this carbon, 1 bond to this other carbon. That's 2 bonds. So 2 electrons for this atom, plus 2 here is 4, plus 2 here is 6 electrons. Okay, so nitrogen is in group 5. It's supposed to have 5 electrons in the valence shell. This one has 6 electrons, so it has an excess of 1 electron. What is the formal charge of this nitrogen? -1, correct. Okay, so -1. Okay, so as a summary of these guys, I'll show you how to calculate formal charges. Okay, think about the group number that give you the valence electrons. Look how many electrons are in the valence shell of that specific atom, and then you can tell the formal charge. Okay, to tell how many electrons in the valence shell, you just need to look at the bonding electrons and the lone pairs. Okay, so in general, an oxygen with 2 bonds is going to be neutral. An oxygen with 3 bonds is going to be positively charged. An oxygen with 1 bond is going to be negatively charged. And nitrogen with 3 bonds is going to be neutral, 4 positively charged, 2 negatively charged. Carbon with 4 bonds neutral, 3 positive, 3 and a lone pair negative. Okay, these are the molecule, the atoms. Yes, the carbon ion isn't stable because it has an excess of electrons and it's too much for the carbon to hold it by itself because the carbon is not very electronegative. Okay, so it will react pretty quickly. It's not as unstable as a carbocation though, but it is quite reactive too. Okay. All right, guys. So any questions? I think somebody had a hand raised. If you had a question, feel free to ask now. Okay, so no questions. So as a summary of this first section, I expect you guys, and I'm gonna write it over here, to draw organic molecules using condensed formula, structural formulas, and obviously line and angle notation. And you must be really good at that. And I'm expecting you guys to provide Lewis structures of these organic molecules, meaning you need to know which atoms you have to add dots on them. And I also expect you guys to be able to tell the formal charge of organic molecules once you are given the Lewis structure. Okay, so this is a must. It will be in the exam. It's one of the main concepts and main yeah, goals of the class for you guys to know before you move into organic one. Because that way, whenever you look at an organic molecule, you'll be really good at telling exactly not only the how the molecule is, but also the electron distribution and the reactivity and geometry as well. Okay. All right. So now that we're talking about all this, and I think I showed in the previous class that carbons can form double and triple bonds. I want to then talk a little bit more about that because now we are more prepared to talk about different types of bondings in carbon, okay, in general. So I'm going to draw here a very simple organic molecule. Okay, how many carbons in this molecule, guys?
1.
1 carbon, right? Here is another molecule. How many here? How many carbons here? 2 carbons. Here we have another 2 carbons, okay? So let's start looking at the type of bonding the carbon is using for bonding to these hydrogen atoms or these carbon atoms, okay? Because that's going to be our next goal, to really understand now bonding and geometry of these molecules based on the understanding of bonding. Okay, so in this carbon over here, I'm going to write that we can see, obviously, this carbon has 4 single bonds, okay? So that carbon has 4 single bonds. Uh, Whenever you have a carbon with 4 single bonds, or whenever there is just one bond in between 2 atoms, could be, let me give you an example so you can see what I'm saying. Let's say I'm going to draw just another molecule, any organic molecule. Let's say this. In this molecule, how many carbons do we have here? 5 carbons, right? Every carbon here is bonded to another carbon through a single bond, and they are bonding to 2 hydrogens, 2 hydrogen, 3. So every bond in this molecule is single. There is no multiple bonds. There is no double or triple bonds here. That's what I'm trying to say, okay? So whenever you have only single bonds, just one bond in between 2 atoms, that bond will be sigma. Sigma stands for cylindrically symmetrical. And again, uh, 4 single bonds, 4 sigma bonds. Hmm? So what exactly do I mean by a sigma bond? I'm going to show you the drawing here so you know exactly what I'm talking about, okay? So a sigma bond is when you have, and I'm going to write it over here, a direct overlapping of atomic or hybrid orbitals. I get into, you still don't know what is a hybrid orbital, so we will get into that in 5 minutes. But you don't need to know that at this point to understand what I'm saying. So it's direct overlapping of 2 orbitals, and these orbitals could be atomic or other type of orbital. It doesn't really matter. The point being is when you have a direct overlapping of 2 orbitals, uh, we call this new orbital a sigma orbital, okay? And that's very important because once again, sigma stands for cylindrically symmetrical. So you can see how in any sigma bond, guys, there is, and I'm trying to show here, there is across the axis of the atoms, uh, you have electron density. Okay, sorry, I'm gonna do a better drawing. So across the axis of the atoms, there is electron density, and that's the axis of the atom, and we call this cylindrically symmetrical. The electron density is right in between the 2 uh, atoms, right here. There is electron density here, okay? So that's the type of bonding that we call a sigma bond. It's a sigma is cylindrically symmetrical, direct overlapping of 2 orbitals. So they are in direct contact with one another. We call that a sigma bond. Everybody really have to, want you guys to really understand this. And whenever you see a carbon atom having only single bonds, all these single bonds will be sigma, okay? Somebody's asking, are the non-shaded portion of the sigma bonds of the atoms? Okay, remember this is a sigma orbital, okay? which means that the non-shading has a different wave sign of the wave function, but there is electron density there as well. Okay, keep that in mind. So whenever you think about a sigma bond, once again, guys, direct overlapping of two orbitals, we can say just like that for now. And any carbon having 4 single bonds, every single bond will be sigma. Yes, right here there is a node, and right here there is a node. To change in the wave, in the sign of the wave function. Now, let's move into this molecule here. So these carbons here, there is a double bond in between these two carbons. So whenever we have a double bond, one bond will be sigma, exactly as we just discussed, looking exactly like this. And the second bond will be pi. In a double bond, one bond is sigma, one bond is pi. Obviously, uh, there is in between two atoms, there is only room for one sigma bond, right? The electron density in between the two atoms, that's it. No more room, physical space for an extra sigma bond. So the following bond, when you have a double bond, cannot be sigma, it must be pi. Okay, so let's define exactly what is a pi bond. A pi bond is quite different from a sigma bond, and we will define a pi bond as side-by-side overlapping of pure p orbitals. That's a pi bond. Side-by-side, so this is direct overlapping. This is side-by-side overlapping of pure p orbital. I said here of two orbitals, could be anything. We are gonna get into that later, but what I do want to emphasize here is that for the pi bond, it only takes place through pure p orbitals, just p orbitals. No other orbitals can form a pi bond except for the p orbitals. Okay, so remember when we discussed about the electronic distribution of carbon and the elements of the second period of the periodic table. How many orbitals do we have in the second shell? How many orbitals, guys, do we have in the second shell? Orbitals. How many second shells? 8 electrons. How many orbitals? 4 orbitals in the second shell. What are those orbitals? Anybody remember? You must know this at this point. What are the orbitals in 1s and 3p, right? So we have in the second shell, we have a 2s and then 2px, 2py, and 2pz. Okay? Correct. So for the 3p orbitals, what is the angle between them? We discussed that also in the first or second class. What is the angle in between the p orbitals? Always 90 degrees is the angle in between the p orbitals. Remember how I show you here. So I'm a little surprised that not many people are answering. I hope you guys are following and paying attention. If you are not, or if you have questions, please ask. Don't like to see only one or two people writing on the chat. I want to make sure that you guys are active. That's something about this online classes that I really hate. I don't really know what's going on the other side. So this is the 3 p orbitals, guys. I made this drawing in the first class. I said this is like axis X, Y, and Z, okay? 90-degree angles, and we said that they are orthogonal because of that, meaning that they have 90-degree angle, okay? So why am I emphasizing on this? Because I'm just talking about pi bonds and saying that the pi bonds is a side-by-side overlapping of pure p orbitals, okay? Now, for two p orbitals to form a pi bond, they must be, this is a requirement, properly aligned, meaning that they must be parallel and in the same plane. Very important. So that actually means that for one atom, the three p orbitals will look like this. For the atom number two, the one that is bonding to the first one, the three p orbitals will look like that. So this one here, the Z, can form a pi bond with the Z of the other atom. The blue with the blue, the red with the red. But the blue cannot form a pi bond with the red because they are not in the same plane. Okay? This one cannot form a pi bond with the red, not in the same plane, neither with the blue. So they must be parallel and in the same plane. So properly aligned. Okay? That's very important. So you really got to understand a pi bond means side-by-side overlapping of pure p orbitals, and the p orbitals to form a pi bond must be properly aligned. They must be parallel and they must be in the same plane. Otherwise, there will not be any interaction in between these two orbitals. Is that clear? Any questions? So according to these two, which bond will be stronger, sigma or pi? Which one do you think is a stronger bond? So sigma is a direct overlapping. So that bonding is stronger as the pi bond, which is a side by side. So let me tell you what a side by side means here for this molecule. We'll go to the triple bond later. Okay. So for this molecule here, side by side means I'm gonna draw the molecule slightly different here. So what I'm gonna draw is now the same molecule showing as lines the sigma bonds, and then I'm gonna make a draw for the pi bond. So the pi bond, as I said, is side-by-side overlapping of p orbitals, which means, guys, that any molecule with a double bond, okay, will have a cloud of electrons above and below the plane of the molecule. Okay, that's why, that's exactly what side-by-side overlapping means. The moment that I'm talking about a pi bond means that there is electron density in this area here. That's why I'm using this drawing. And electron density in this area here. That electron density is the result of a pi bond. And as you can see, can only happen when the two p orbitals are properly aligned. So a pi bond can only arise from the interaction, the side-by-side interaction overlapping of two properly aligned p orbitals. And it will look like this. It's important for you guys to see how the bonding looks like, okay? So this is how a pi bond from a double bond will look like. Okay? So what I want to also show you now is the following. In this molecule here, where we have four single bonds, four sigma bonds, there are four clouds of electrons around these carbons. Electrons repel each other, as we know, because they are negatively charged. So I want to talk now about the geometry of these molecules. And you can imagine that if there are 4 clouds of electrons around this carbon here, the ideal 3D shape for that carbon to keep these clouds of electrons as far as possible from one another would be a tetrahedral structure. Okay, so any carbon with 4 bonds, the 4 bonds are sigma, and the geometry of that carbon will be tetrahedral, meaning that the angle, bonding angle, is 109.5 in between every sigma bond. Okay, any questions so far? That's a tetrahedral structure. Okay, guys, it's important for you guys to see that. Let me see. Okay, good. All right, so if we talk about now this double bond, carbon-carbon double bond, one bond is sigma, as we just discussed, direct overlapping. The second bond is pi, which looks like this. So there is a pi bond, and the cloud of electrons for this carbon is 3 sigma bonds, 3 clouds of electrons. For 3 clouds of electrons, the optimal geometry to keep them as far as possible is called trigonal planar. So the molecule is really flat, okay? And the angle in between each bond is each sigma bond is going to be 120 degrees. That's a trigonal planar bond. Okay. See if I can show you a better picture of that. Not sure I'm going to be able to, but okay. So here is a trigonal planar. See, this carbon oxygen here is a double bond, okay? So 3 clouds of electrons, this is how it looks like. Trigonal planar, 120. So there is a flat structure, and there is an electron above and below this double bond here. Okay, that's what trigonal planar means. The tetrahedral structure will look like this. Okay. So this will be the tetrahedral structure, and this one will be the trigonal planar. See if I can show you a better picture of a trigonal planar, because I really want you guys to be able to see that in 3D well. So this will be the 3 sigma bonds of the 3 sigma bond of the carbon-carbon double bond, okay? So this carbon will be this one here, right in the center, okay? The angle in between each sigma bond will be 120. And above this, then you will have the pi bonds, cloud of electrons up. So the molecule is flat, and there is a cloud of electrons above and below. If I try to make another drawing, I'll try later, but that's the idea, okay? If you guys have questions or you cannot see well, just let me know. And then there is the third option, which is the third possibility you find in organic molecules. Once you have a carbon-carbon with a triple bond. In a triple bond, how many sigma bonds should I expect to have in a triple bond, guys? One, because the maximum number of sigma bonds that I can have in between two atoms is one. So one bond will be sigma, and the two remaining bonds will be pi bonds. Okay, so no, that's a good question, Iman. So one pi bond has just one orbital, but is a result of the combination of two p orbitals. Okay, the pi bond looks like this. Okay, and it looks with like this, exactly like this. You have a nodal plane across the plane of the molecule. So electron density above and below. Okay. So when you have a triple bond, there is one sigma bond and two pi bonds. As I said, pi bonds are the result of side-by-side overlapping of p orbitals. So in this specific case, one pi bond will be, as we showed before, the second pi bond will have to be perpendicular 90-degree angles from the first pi bond, because we know that p orbitals are 90 degrees angle from one another. So I'm going to draw it like this. Okay, I'm going to color code this so you can see how one pi bond will be through the two p orbitals that are parallel, and the second pi bond through the second set of p orbitals that are 90-degree angle from the first one. Guys, so it looks, so you got to look at this in 3D as the blue shaded orbitals going from the screen behind the screen, and then the ones that are not unshaded toward you. Okay, so this is coming toward you, this area over here. This is going away from you, 90, so perpendicular to the screen. This is on the plane of the screen. Okay, so you have 90-degree angles in between these two pi bonds. So that's really important, because, and I'm going to show another picture here so you can see exactly what I'm talking about. Um, so you can really understand the nature of this molecule. So this is how, uh, so one pi bond will be with this p orbital, second pi bond with this p orbital, okay? So these molecules, the geometry, because you have only two sigma bonds around each carbon, around this carbon is two sigma bonds, so the geometry of this molecule will be obviously linear, and the bond angle will be 180 degrees. So whenever you think about these triple bonds, you gotta think about these two sigma bonds will be 180 from this sigma bond. So it's linear, this molecule. And there is a cylinder of electrons around this carbon-carbon, resulting from these two pi bonds, okay? So that's more or less how they look like. I'll show you another picture in a second, so you can see exactly what I mean by that, okay? And again, is any question? The geometry is what the molecule looks like in 3D. Okay, so what is the bonding angle in between each bond? Where are the electrons of this specific? So the geometry of this molecule is trigonal planar. For the last example, linear. It's linear. Okay, show you how the molecule looks like right now. See, 1 second if I find a better picture to show you exactly what I mean. And one thing that can help you to envision this is when you look at the models. So if you use the molecular models, it will be pretty helpful. Um, Molecule looks like literally like 180 degrees. Okay, so you have like a series of electrons. This is the what I mean by linear and the 180 degrees angle. See? So there's 180 degrees in between the sigma carbon sigma and carbon hydrogen sigma. The angle is 180. And you have pi bonds above and below and then coming toward you and away from you. So a cylinder of electrons around the carbon-carbon bond. So it could be something like this. And I'll show you right now. That could be how this molecule looks like. Okay. Any questions so far? No? Everybody is okay? Okay, so I want to then take a deeper look at the bonding in these molecules, and this is what I just told you right now. It's a way of looking at when you have an organic molecule with four bonds, and so sorry, with four single bonds, double bond, and a triple bond. Okay, you gotta think about whenever there is a portion of a molecule, because this is a very simple example, but then when you have more complex molecules, you might have double bonds, triple bonds, single bonds in the same molecule. So you got to think about each section of this molecule having a different geometry. Okay, the carbon with four bonds will be tetrahedral. The carbon with double bond will be trigonal planar. Those with a triple bond will be linear. Okay, so uh, now we got to think about what kind of orbitals is the carbon atom using for bonding, for example, these four hydrogen atoms. What kind of orbitals is this carbon bond using to be bonding to these two hydrogens and to this carbon? The pi bond we know is a p orbital. The remaining three, we have to understand that. Same applies here. What kind of bond of orbital is this carbon using to bind this hydrogen through a sigma bond and this other carbon through a sigma bond? The remaining two p orbitals we already know is this, but we don't know yet what are the orbitals that the carbon is using for the sigma bonding. That's also very important, okay? And in order to understand that, we're gonna look at what we call valence bond theory. So here is the electronic distribution for carbon. Carbon is in group 4, period number 2. If it's in second period of the periodic table, obviously a valence shell is shell number 2, and we know that in shell number 2 there are 4 orbitals. The 2s and 2p orbitals. So nothing new. You guys know this. I'm gonna label this as 2s, and here we're gonna have the 2p. And you should know at this point that one of them is px, second one py, and the third pz. That's not a big deal, okay? And there are how many electrons in the valence shell of carbon? We have 4 electrons in the valence shell of carbon. So we have here 1, 2, 3, and 4. So this could be the valence shell of the carbon atom. And write this carbon. Okay, valence shell. So guys, as I said, a carbon with 4 single bonds, all the bonds are sigma. I'm gonna copy this so you follow what I'm talking about. So A carbon with 4 single bonds, all the bonds are sigma, right? And I said that the bonds in between the p are 90, so you can imagine that if this carbon is going to bond 4 hydrogens, it has an empty orbital here, which can allow 2 electrons, and 1 electron here, 1 electron here. So if anything, it could form 3 bonds, and the angle in between the bonds will be 90, not the reality, because we know for a fact and experimentally that the angle here is 109.5, right? So the molecule looks exactly like this. But bottom line being that the real structure of this molecule cannot be explained for the sigma bonds if carbon were using the p orbitals for this bonding. The p orbitals are only used for pi bonds, no pi bonds here. So what's going to happen is we're going to call this process hybridization. So what exactly do I mean by that? So before the carbon atom bonds to each of these hydrogens, the atomic orbital carbon will be hybridized. And I'm going to write it over here. Before bonding, the atomic orbitals of carbon will be hybridized, meaning they will be combined to form hybrid orbitals. And combination, guys, and this can get more complex. I don't need you guys to go too deep, but just for you to understand a little bit deeper, combination means that, remember, each of these orbitals is a math equation. So combining means adding these 4 equations and then getting 4 new solutions. That's what combination means. So before the carbon bonds to hydrogens to form a new molecule, the atomic orbitals of carbon will be hybridized, will be combined to form hybrid orbitals. So there are rules for this combination, and the first and most important rule is uh, you get the same number. So if you combine, if you hybridize 4 atomic orbitals, you get 4 hybrid orbitals, meaning that you get the same number of hybrid orbitals as atomic orbitals you combine. If you combine 2, you get 2. You combine 3, 3, 4, 4. Okay? So for a carbon with 4 single bonds, it has 4 sigma bonds. So the carbon is going to combine the 4 atomic orbitals. If I combine 4 atomic orbitals, I'll be getting 4 hybrid orbitals, because you always get the same number. And because we're combining 1s with 3p, we are going to call these 4 orbitals sp3 orbitals. So the hybridization of 1s and 3p orbital leads to 4 sp3 hybrid orbitals, and each of these orbitals is going to be occupied. So there is a total of 4 electrons. So I will just place 1 electron in each orbital. Okay. So the shape of a hybrid orbital is something like this. Of a hybrid sp3 orbital, it looks like this. Okay. That's the shape of a sp3 orbital. So you have 4 of them. I'm going to show another cartoon here so you know what it looks like. Once again, that's very important. That's how sp3 orbital looks like. Okay. And these are the orbitals that the carbon are going to be using for the sigma bonds to these hydrogen atoms, 4 sp3 hybrid orbitals. Now, when you plot these 4 sp3 hybrid orbitals, and this is now quantum mechanics, and it's a math equation, so you do the plotting and resolve, and beautifully, the plot of that comes to a tetrahedral structure. And the angle continues to be 109.5. So this is like a scientific way to explain what I just said before. Okay, so 4 single bonds are 4 sigma bonds. For these sigma bonds, the carbon will be using an sp3 hybrid orbitals. And the angle in between these sp3 hybrid orbitals is going to be 109.5. It's a tetrahedral structure. So guys, it's important for you to realize what is the bonding here. So this bond here is a sigma bond, and that sigma bond is from an sp3 hybrid orbital from the carbon and an s orbital of the hydrogen. So this is a sigma sp3s bond. And obviously the 4 of them will be sigma sp3s. Okay, if you have a molecule, let's say like this, all the bonds here are sigma. Carbon is using hybrid orbitals for all these bonding. So this carbon over here, for example, is bonding to the carbon on the right. So this is a sigma bond, carbon-carbon. So this would be a sigma because both carbons are using sp3 hybrid orbitals. That would be a sigma bond sp3. So in any organic molecule with single bonds, carbon-carbon, the sigma bonds will be sp3. Both carbons will be using sp3 hybrid orbitals. And the bonds towards hydrogens will be sigma sp3s because hydrogen obviously will be using s orbital. Hydrogen cannot hybridize because it only has one orbital, 1s. Any questions? Okay, so when you have, let me minimize this because I'm gonna need more space. So that's the case for, once again, when you have a carbon with 4 sigma bonds. So second scenario could be when there is a double bond in between 2 carbons. I said when there is a double bond, one bond is sigma and one bond is pi, right? So right here we have a sigma and a pi bond. So let me copy back again here the electron distribution of carbon so you can see exactly what's going to happen. So this is the electron distribution for carbon. As I said, before this carbon forming any bond, before any of this carbon forming any bonding, the orbitals, the atomic orbitals of carbons will be hybridized. Now, we call hybridization. So by the way, guys, what will be the hybridization of this carbon over here? So that carbon will be sp3 hybridized. How do I know? Because that carbon only has single bonds. And as I just explained, a carbon with only single bonds is going to use its 4 atomic orbitals for bonding, hybridizing the 4, so getting 4 sp3 hybrid orbitals. So that's an sp3 hybridized carbon, and we know that also that carbon is tetrahedral. Okay, that's an sp3 hybridized carbon. The one on the bottom, which only has single bonds, will also be sp3 hybridized. So the 4 sigma bonds of this carbon, the 4 sigma bond of this carbon will be through sp3 hybridized orbitals. What about these two in the center? So these two right here, they have a pi bond in between them. So for the pi bond, as I said before, the pi bond must take place through a pure p orbital. So we must save one p orbital for the pi bond, because there is a pi bond, and the pi bond will only take place through pure p orbitals. So if I save one p orbitals for the pi bond, how many orbitals do I have remaining in the carbon atom? If one of them is saved for the pi bond, how many do I have remaining for hybridization? Okay, so there will be 3 remaining. One is saved for pi bonding. There are 2p and 1s remaining. Okay, so combining 1s and 2p, if I combine 3 atomic orbitals, I will get 3 hybrid orbitals, because I am combining 1s and 2p. These 3 orbitals will be called sp2. And then obviously there will be 1 electron for the pi bond. Okay, so any carbon with a double bond will be having 1 pi bond through the p orbital, and the 3 remaining sigma bonds will be through hybrid orbital sp2. So these carbons will be sp2 hybridized. And if you superpose these sp2 orbitals, they will come to a perfect trigonal planar shape. Bond angle will be 120, as I said before. So both carbons will be sp2 hybridized, meaning they will be having a pi bond through a pure p orbital from each carbon, and the 3 sigma bonds from each carbon will be through sp2 hybrid orbitals. That actually means that if I, once again, guys, look into the sigma bond here in between these two carbons, I'm going to say that's a sigma sp2 sp2, because each carbon will be using an sp2 hybrid orbitals for the bonding. Okay, and then finally, when you have a situation with a triple bond, for any carbon having a triple bond, we already know that 2 bonds are pi. If 2 bonds are pi, it means that I must save how many p orbitals for the pi bonds in this case. So if two bonds are pi's, how many p orbitals should I save for the pi bond? Anybody want to answer? You guys, are you guys there at all? Okay, so for the triple bond, how many p orbitals should I save for the pi bonds? In this carbon, for example, how many p orbitals should I leave out? Two should be used for the pi bonding because I have two pi bonds. If two must be saved for pi bonds, I have only two remaining, one s and one p for hybridization. Hybridization, therefore, in that case, if I combine one s and one p, I will get two sp hybrid orbitals. And the sp hybrid orbitals will be the ones that will be used for the bonding. So whenever you have a molecule with a triple bond, the sigma bond in this triple bond from each carbon will be the result of sigma sp sp. Why is that? Because once again, before carbon bonding to any other atom, the atomic orbitals of carbon will be hybridized. So the only thing that you need to look is how many pi bonds do I have in that carbon? If I have none, the four atomic orbitals will be hybridized. I get 4 sp3. If I have one pi bond, then only three atomic orbitals can be combined, so I get 3 sp2. If I have two pi bonds in that carbon, only two atomic orbitals can be combined, leading to two hybrid sp orbitals. Those are the orbitals that the carbons will use for the sigma bonding. And when you plot these hybrid orbitals, the geometry of the molecule comes to exactly what I just discussed. Tetrahedral structure for the single bonds, trigonal planar for the double bond, and linear for the triple bonds. Okay, so it's very important, guys. And so we say before, when we look at a molecule like this, we said that hybridization of this carbon and hybridization for these carbons are sp. So these carbons are sp hybridized. And everybody now in chemistry knows what that means. It means that it's using sp hybrid orbitals for the bonding. It means that the molecule is linear, right? The carbons on the ends are obviously all single bonds, so these are sp3 hybridized carbons, all single bonds. Okay, so when I look, guys, at, and I'm gonna just, so when I look at the sigma bond here in between this sp3 and the sp carbon, that sigma bond will be a sigma sp sp3, meaning that the orbitals participating in this sigma bond, which is a direct overlapping in this case of hybrid orbitals, one hybrid orbital will be an sp from this carbon, and the second orbital participating in the bonding is a hybrid sp3 from this carbon. It's the sigma sp sp3. Okay. All right, guys. So I'm gonna stop the recording here.